Hello, welcome to the NPTEL course Fundamentals of Composite and Cellular Materials. In today's lecture, we will discuss about some other important properties of the foams. In the last several lectures, we discussed about many properties of foams. We started with the deformation behavior of foams, where we learnt about the mechanical properties of foams, especially under compression. Like we learnt in detail how the open cell foams, closed cell foams and honeycombs they deform under compression, and we also learnt about the influence of the strain rate, temperature, indentation behavior, their fracture mechanics and all those things. In the last lecture, we learnt about the thermal properties of foams. We learnt that the thermal properties of foams are very important, and there are many applications like heat exchanger applications or thermal insulation applications where the thermal properties of foams are very important. We learnt about several thermal properties like melting point, expansion coefficient, specific heat, thermal conductivity and thermal shock resistance. There we learnt that both melting point and expansion coefficient, they are actually porosity independent. That means, both melting point and expansion coefficient, they do not depend upon the amount of porosity, and these values are actually similar or identical to the properties of the bulk material of which the foam or cellular solid is made of. In contrast, thermal conductivity and thermal shock resistance, they depend strongly upon both porosity and also pore shape. Among them, conductivity is extremely important property because it depends upon many structural parameters like the foam, the cell shape, the amount of cell material and also the cell dimensions, temperature and so on. The thermal shock resistance, we learned that it depends upon many factors and also some mechanical properties like the Young's modulus and Poisson's ratio, they actually control the thermal shock resistance. For thermal shock resistance for ceramic materials, we learned that the material should have a low expansion coefficient and also a low modulus, and also the material should have a high fracture toughness to have sufficient thermal shock resistance. In today's lecture will be the last lecture where we will discuss about the different properties of foams, and in this lecture we discuss about some less important properties or less studied properties like electrical property and the acoustic property, and finally the energy absorption behavior of foams will be discussed, and this is again a very important application of foams because we learned initially that especially for polymer foams and metal foams, these foams are very attractive for energy absorption applications like for crash applications or for packaging applications. They are actually the energy absorption of foams is very important, and in this lecture we will learn the basics of how these energy absorption behavior of foams are studied and how the typical construction diagrams for energy absorption are created for foams will be discussed briefly. The main keywords for this lecture are electrical properties, acoustic properties, energy absorption, plateau absorption, energy absorption diagrams and critical damage stress. So, we start with the electrical properties of foams. So, just like foams are very attractive for thermal insulation materials, there are also applications of foams where the electrical insulation properties of foams are very important. That means, there are many applications which actually aim to have as much as electrical resistivity of the foams or of the structure as possible. Now, this diagram or this picture over here, this actually shows the variation of the electrical conductivity in various classes of materials starting from rocks to many like metals and ceramics. And as we know that typically polymers have low electrical conductivity and high resistivity, while many of the metals like copper, then silver, they have also very high electrical conductivity. Also many ceramics like graphite or carbide ceramics like silicon carbide and others, they also have sufficiently good conductivity. Now, in case of foams, actually the conductivity of the foams again depends upon the amount of porosity. So, as you already mentioned, I mentioned it so many times in this lecture that when we study the foams, one of the most important properties is the relative density. That means, the density of the foam divided by the density of the bulk solid, this actually controls the relative density of the foams, and this has a direct relation to the to several properties of the foams. And again, if we consider the resistivity of the foams, which is the inverse of the conductivity, that means if we consider this R as the resistivity, then R is actually nothing but 1 over the conductivity. So, basically as you can see over here, the higher the foam porosity, that means the lower the value of the relative density rho star over rho s, the more will be the resistivity. That means, if we want to have a highly resistive foam, then we have to have very high amount of porosity in the material, because of two reasons. One is that the pores, because they are filled up with the gas, they have inherently a low conductivity or high resistivity, and additionally as we increase the amount of porosity in the material, there is also more tortuosity in the structure, and that will again reduce the conductivity or increase the resistivity of the material. So, for electrical insulation applications, just like the thermal insulation applications, the aim is to have the foams with as low density as possible. Next are the acoustic properties of foams. So, if you remember that when we discussed about the applications of foams towards the beginning of this course, we learned that one of the most important applications of foams are as sound absorbers, because as we know there are many applications where sound absorption is very important, especially for example for houses, or like beside the autobahn or beside the highways where high speed trains go, or high speed vehicles actually run. In those areas actually sound absorption becomes very important. And we learnt in the last lecture that again this sound, in this I mean many properties of the foams depend upon the type of the cell structure. We learnt that, I mean as we know that the foams can have either open cell foam or closed cell foam. And the closed cell foams we learnt in the last lecture that if you want to have a good thermal insulation property, then the closed cell foams are very attractive. Whereas, in case of applications where we need like sound absorption, in those applications actually the open cell foams are more attractive, because as we can see in this schematic diagram over here, the sound absorption actually means that whenever a sound is incident, that means we can see over here, this is the incident sound energy and this is actually one surface. So, three factors or three things can happen. That means the sound can actually reflect, if it is a solid material, the sound can actually reflect to the material. Then if it is a very kind of like, if it is a very if the pores are like along this direction, for example, like if the pores are aligned like that, then also because the sound wave is actually kind of parallel to the pore alignment. So, the sound can easily transmit. That means, in both these cases, if the sound is easily reflected or it is easily transmitted to the material on which the sound is kind of incident, in those cases we have less amount of sound energy absorption, because by absorption we mean that what is the actual amount of sound energy which is absorbed inside the material by some conversion, like either to heat or some other energy, the sound will be converted. And for that we actually need first of all an open cell structure, and then we typically need a structure where the structure will have continuous tortuosity. That means, because we need a structure like something like this where the cell walls or the struts will have continuous dimensional changes, and these will actually make lot of reflections and absorption. That means, if the structure is irregular, if it is not like an uniaxial or kind of a unidirectional pore structure, then the sound wave as it passes through the material or as it enters the structure, it will actually get reflected by continuous interaction with the various cell struts, and that will actually play a very big role in actually absorbing the sound wave. Okay? That is why the irregular pore structure or kind of continuously changing pore structure is very attractive for sound energy applications or sound energy absorption. So, there are various mechanisms through which sound actually gets absorbed inside the material, and there are 5 mechanisms have typically been identified, and these mechanisms are shown over here. Now, after the sound absorption, one very important application of the foams that is very very commonly used, and especially for two applications, like one for the automobile industry in the high end automobiles, and also for day to day packaging applications, like whenever we purchase a very kind of high value electronic like a laptop or whatever, we often see that the laptop case or the main component is actually covered with a polymer foam or the polymer or a polymer, because this polymer foam is actually playing a big role in actually protecting the valuables in the inside, because these are actually for the crash protection or any kind of accident or any kind of shock wave. Then these polymer foams or whatever this packaging is there, they will actually they will undergo deformation themselves, and they will actually absorb the whatever crash energy is there, and by doing that they will actually protect the valuables inside the packaging. Also for automobile applications, we learned that again in automobile applications very often we use metal foams, like aluminum foams are very famous for these applications, because whenever there is a front end crash or kind of a crash from the on the side of the automobiles, then the bumpers or the doors of the automobiles, they can actually be filled up with the foams, and again the foams, the main aim is that the foam material will actually undergo deformation. That means whenever there is a very high velocity crash, it is considered that the foams will undergo deformation, and by doing so it will actually absorb the crash energy, and by doing that it will actually protect the inhabitants or the occupants of the car from the actual crash energy. Now, because of these things, as we already learned, that we also see in the next few slides, the deformation behavior of the foams are very important. We learnt about them in detail in the last few lectures, and we will also go through some details in this lecture. But what are the most important properties for the foams if the foam needs to be used for energy absorption applications? The one thing is that one very important point is that the energy, that means this crash can take from any direction, and that means the package must be able to actually absorb the impact from any side. That means the isotropy of the foams is very important in this application. Second thing is that the foam, or whatever this material we are using for crash absorption, they should not increase the weight of the actual component. That means even if we are using a polymer foam for our valuables packaging, or an aluminum foam for the automobile protection, they should not increase the weight of the automobile or the package, because if the automobile weight is increased, again we have less fuel efficiency, for which actually we go for the lightweight construction. So, that means the low density of the foam is again very important factor. And another important thing is that the foams should not be expensive, because after all the main function of the packaging is to give protection. That means they actually do not function or do not perform any function for which the component has been purchased or the component is being used. Their sole function is to give protection, and they are actually sacrificial components, because if there is a crash, these foams or cellular materials will be sacrificed, and while doing that they will protect the occupants or the valuables inside. That means the main or the cost of the foams there should not also be too high. So, these are the main properties required for the energy absorption behavior of the foam or cellular solids. Now, the question is, how do foams actually provide the energy absorption behavior? So, these we discussed in one of the previous lectures in brief detail, and in today's lecture we will discuss about this in much more detail. So, as you can see, this curve or this plot, typical stress strain plot, is being shown over here, and as you can see over here, this is again under compression, because I mentioned several times that the main applications of these foams or cellular solids is under compression, because as these materials have significant amount of pores inside it, if we put the material under tension, then the pores will actually act as the stress raisers, and the material will actually fail or crack very easily. However, when we go for the energy absorption or other applications, the compressive behavior of the foams, because under compression the foams the pores are kind of compressed, and they collapse upon each other, and that will actually give rise to very high amount of deformation depending upon the type of materials being used. Now, just assume that we have a metal which is having a stress strain plot, like, I mean, we can also expand it like this, because if it is a metal, then we typically expect elastic plastic behavior. So, initially in the stress strain plot, initially we have the linear elastic region, say we have the Young's modulus in this place, and then this point, as you can typically see, this is the sigma y, or the yield point of the material. That means, and as we also know that whenever we deform such a material, the energy absorption during deformation is the area under the stress strain plot. So, now just imagine that for whatever application, like for whatever intended application, the critical stress is this point over here. That means, this is the critical stress, we write as sigma c over here. What is the value of the critical stress? For example, just imagine that we design a car, okay, and there are actually relations which the automobile engineers often follow, which actually predict that if there is an head on collision or a clash at a certain velocity, then what will be the amount of stress generated. That means, what will be the stress required to protect the internals of the car component. So, this stress, this critical stress is the sigma c value which we define over here. Now, we also learned about the deformation behavior of the foams in the previous lectures. As we know from that, the deformation behavior of the foams typically have this 3-stage stress strain plot. We initially have a stress strain in the plot, we initially have again a linear elastic region, but the slope of the curve in this region is much smaller than this this E value over here. That means, if this is the E and this is our E star, then we know that E star is much lower than E. Why? Because again this is a function of the relative density. The lower the relative density of the foam, the lower the value of the E star. But after this initial value, we know that this is the most important property of the foams, or that as we continue the deformation, the stress remains more or less constant. So, in practice we have learned that the stress typically rises continuously, but the rate of the rise is pretty slow, and if the density of the foam is very low, then we can expect this plateau region to be very long, typically up to 70 to 80% deformation. And after that, when the foams or the foam have deformed a lot, then actually when the opposing cell walls actually is touching each other or coming in contact to each other, then the foam stress starts to increase, because again at this point now this actually tend to the value of the E. That means, it is not E, but we can write that this slope in this curve or in this region tends to the value of this E value. That means, when the opposing cell walls of the foam are touching each other, then actually the foam starts densifying, and the local modulus or the modulus tends to the value of the modulus of the bulk material, and this region is called the densification region. Now, the important thing is that we defined our sigma c as the critical point over here. So, we also learned that at this sigma c, for the bulk material, when it is compressed, we only have this hatched region, only this much energy will be absorbed, because the bulk material, it is still undergoing elastic deformation, there is no plasticity. So, only this much amount of energy will be absorbed. However, in case of foams, we can see over here that we attain, that the sigma c value is attained at this point over here. That means, as we compress the curve, this is the horizontal value of the sigma c. That means, when we reach the value of sigma c, depending upon the foam density, we have a significant amount of foam deformation, and that will give rise to very large amount of energy absorption, right. And this is the most important application of foams for energy absorption, because it can actually absorb a significant amount of energy at a low value of stress. And we will see afterward in today's lecture that this can again be engineered. That means, depending upon the value of the sigma c that we want to have, we can actually control that what will be the required foam density, and depending upon that we can control what is the amount of energy to be absorbed. And this is only possible because the foams actually provide us with this very long plateau region. Now, the question is, as I just mentioned, the relative density of the foam plays a very important role over here. So, again here we actually compare 3 different foams. So, in this slide we actually compared the behavior of the foam with the bulk metal or the bulk solid of which the foam is made. And there we saw that the behavior of the foam for energy absorption is much improved than the bulk solid. And now we will see that what is the influence of the foam density on the energy absorption behavior. So, now what we do here is that we define an energy W. That means, we define that for our energy absorption application, the amount of energy to be absorbed is W. So, this is the defined energy, and now we have foams having 3 different densities. That means, your rho 1 is the highest density and rho 3 is the lowest foam density. And as you already learned from our previous lectures, the density has a very strong influence on the stress strain plot. As we increase the relative density, what happens? The Young's modulus actually, so with increasing rho, so as rho actually increases, the Young's modulus actually will increase, the sigma c will actually also increase, and the epsilon d, which is the plateau stress, will continuously decrease, right. So, we can actually draw 3 schematic curves over here. That means, rho 1 has the highest density. So, correspondingly this curve over here. So, this curve over here, this has the highest Young's modulus, it has the highest plateau stress, and in this case the densification also starts at the lowest value over here, right. In case of the sigma, in case of the rho 3, which is the lowest density, again the modulus will be the lowest, the densification strain will be the highest, and the plateau stress will also be the lowest among the 3 curves. Now, what is very interesting from these curves is that we see over here, because we have defined the value of the W as constant. That means, in our case, for this particular study, we assume that the task of all the foams is to assume the same amount of energy W. So, what we see over here is that the stress at which this amount of energy W is actually absorbed is different for the three foams. In case of the high density foam or this rho 1 density foam, which is over here, we actually achieve the energy at this stress. So, as you can see over here, this is the value. So, we actually achieve the density as this stress. That means, already the density is pretty high, because the stress required to attain this amount of absorbed energy is already pretty high. In case of, and this happened why? This happened because in this particular case the densification started too early, because this foam has a low density, has a high density. That means, high density means what? High density means the foams, the opposite cell walls will come to contact with each other much earlier. So, that means this foam has a lower epsilon d because of the high density, and because of that it has a high amount of stress required for the same energy absorption, because the foam already densifies at a low strain. What happens to this case over here when we have the lowest density? That means, we have the density of rho 3. Here again we see we have the stress is actually attained at a stress, or the amount of energy absorbed W is attained at a stress which is again pretty close to the value of sigma P1. Why this is happening? Because in this case the density of the foam is too low, right. If the density is too low, that means what? That means it has a very low plateau stress, and in this case, because the plateau stress is very low, it is absorbing from the very beginning, it is absorbing less amount of energy, because the plateau already starts at a low stress, and again when we reach the value of the absorbed energy W, again because of densification, the stress has already become quite high in this particular case. So, in our case we can see that the optimum case in this particular case is the sigma is the rho 2 density foam over here, because in this case the density of the foam is intermediate to rho 1 and rho 3, and that actually leads to a value, because in this case the stress W is actually achieved when the foam is still under the plateau region. That means it is still under the plateau region, and this is the lowest stress at which the highest amount of intended energy has been absorbed. So, you can see that again, depending upon the foam relative density, the amount of energy absorbed varies, and we can actually control how much energy will be absorbed. We can control that by controlling the foam relative density. And based upon that concept itself, these energy absorption diagrams were actually proposed, and these we will briefly go through in today's lecture. So, as you can see over here, as you already know, the amount of energy absorbed is actually a function of the, if we integrate the area under the stress strain plot, we can actually obtain the energy amount of energy absorbed, and this this is the typical plot of the energy absorption diagram, where the y axis is nothing but the volumetric energy absorption W normalized by the Young's modulus of the foam of the solid ES, and the x axis is basically the stress normalized by by ES. And as you can see over here, this inset actually shows the typical stress strain plot. Again, we can see, if we want to absorb or if you want to find out the total amount of energy absorbed, we need to integrate both this area, that means the elastic region, and also the plastic region, right. Now, as we all know that the amount of energy absorbed in the elastic region is very low, right. So, the most amount of energy which is actually absorbed or is in the plastic region, starting from the point where the plateau stress is actually starting, and this plateau, this region, that means this area of the stress strain plot, this plateau stress region is actually defined by these expressions over here. That means these expressions, they are a function of the foam of the strain, and also the relative density of the foam, this rho over rho s. So, these expressions, if they are integrated over the whole strain, then we can actually obtain, using this expression over here, then we can actually obtain such diagrams over here. Now, what is the use of such diagrams? So, suppose we want to see that what happens if we define a particular peak stress value. So, suppose our peak stress value, we take it as a point over here. That means our peak stress value is, that means the peak stress that we want to, it means the foam that we want to design for our application should give optimum protection for a peak stress, which is sigma over ES is equal to 0.1, sorry 0.001, so 10 to the power minus 3. So, this is the peak stress value to which the foam will be deformed, and for that we want to maximize the amount of energy absorption. So, now these curves or this loci over here, this actually gives this amount of volumetric energy absorption over stress for different foam densities. So, as you can see over here, these individual curves. So, this first curve is for density of 0.01, the second curve is for density of 0.02, then 0.05, then 0.1, 0.2, 0.3 and so on. So, what we have to do now? We have to then draw a vertical line from here. That means, if we draw a vertical line from here, so the curve which is cut, the highest curve that is cut in this case is the one for which the rho over rho star is 0.1. That means, we can tell that for this amount of sigma over ES that we want to design the foam for this amount of peak stress condition, the highest amount of energy will be absorbed if the foam has a density of 0.1. If we select a foam, because we always tend to think that for foams, the lower the density, the better it is, because we want to have a porous material. That means, if we increase more amount of pores, it will have better properties. This we may think in this line, but now if we reduce the foam density, say for example, we go for a density of 0.02, then we see that in this case the amount of energy absorption for this peak stress will only be this much, and if we go for even higher foam density, say for example 0.3 foam density, that means this curve over here, there for this peak stress we will attain only this much amount of energy. That means, we can see that for it is very important to actually identify the peak stress, and based upon that, using the energy absorption diagrams, we have to, or we should identify the optimum foam density which will give us this much amount of peak stress. And this, I mean, for each of such curves, if we just join the peak point, that means, join the topmost point of each of this curve, we get this dotted line. Okay? And this dotted line is actually the locus which actually separates the absorption diagram into two regions. One is above this region, which is kind of the region which is called the non-assailable region or non-accessible region. That means, if we have any particular foam density, we cannot absorb more energy than this dotted line. That means, this dotted line actually provides the, for any foam density, this dotted line is the highest amount of energy absorption possible line, and that means, the lines or the regions below this dotted line are the regions which we can actually access by kind of controlling the foam density. And the expression for this dotted line again we can find out, or kind of deduced by these expressions over here. So, we have learned that in case of foams, if the foam has to be used for energy absorption applications, it is very important to identify first what is the peak stress to be designed for. Once the peak stress have been identified from the design specific applications, then we need to use this specific energy absorption diagram to actually find out at which relative density the highest amount of stress will be, or energy will be absorbed, and then the foam should be designed according to that relative density. So, this brings us to the end of our today's lecture. We learnt about 3 different properties in this lecture. We first learnt about the electrical properties, and there we learnt that in case of foams, the resistivity of the foam depends upon the foam relative density. The lower the relative density, the higher the amount of porosity, the more will be the resistivity of the foam, and this is again applicable for insulation applications. Second, we learnt about the acoustic properties. We learned that for sound absorption, the foam should be open cell in nature, and it should have very tortuous pore shapes, because the tortuous pore shapes will interact with the incident sound energy, and by continuous reflection and absorption, the sound energy will be absorbed, and this way the noise pollution can be mitigated. And third, we learnt about the application of the foams for energy absorption. We learnt that it is very important to identify the peak stress of the foam at which the energy absorption should be required, and for that the special stress strain curve of the foams under compression, like the elastic part, then the plateau part, and the densification part is very important, and we need to identify the optimum foam density for these applications, and based on that the optimum amount of energy will be identified. So, the main literature for this lecture are given over here, and in the next lecture or the next couple of lectures we will learn about some advanced materials or some natural materials like wood, which are kind of porous materials, and how the pore structure actually controls the properties, and then in the next couple of the final couple of lectures we will learn about a very new class of hybrid materials, which is the functionally graded materials. Thank you very much.